This is week 2, and it focuses on arrays, memory, and essential programming concepts in C. Let's start with how C code gets compiled into machine code. In CS50, the compiler we use is called Clang. There are 4 main steps in the compilation process. Step 1. Pre-processing. This is where all header files are included and macros are expanded. Step 2. Compiling. The C code is translated into assembly language. Step 3. Assembling. The assembly code is converted into machine code or to binary. Step 4. Linking. This is where different compiled files, like hello.c, CS50.c, and standard input-output.c, are combined into one executable program. Now let's talk about debugging. The term bug actually comes from a real insect found inside an early computer. CS50 provides a built-in debugger, similar to the one in Visual Studio Code. With breakpoints, we can pause the code at a certain line and inspect what's happening. We also saw something called garbage values. These are random numbers that show up when you declare a variable, but don't initialize it. Next, let's explore memory and data sizes in computing. 1 kilobyte equals 1024 bytes, not 1000 because of binary addressing. Each int in C uses 4 bytes of memory, or 32 bits. So, an array of 3 integers would take up 12 bytes. Let's move on to arrays. An array is a collection of values stored in consecutive memory locations. You can declare an array like this. Integer score 3 to access elements inside an array. We use an index. Remember, indexing starts at 0, so scores 2 gives us the third element. We can also create 2D arrays, which are useful for grids, games like chess, or more complex data structures. Now, let's talk about strings. In C, a string is just an array of characters. Here's an example of 3 characters. To print them we use printf%c for each one of them. But if we use %i instead of %c, we'll see the ASCII values 72, 73, and 33. Characters and integers are closely related. They are just number behind the scenes. In memory, each byte store a value of that character, which can also be represented as an integer. String do similar thing by storing multiple values inside of it, and it always ends with a special character, the null terminator. It looks like this, \0. This tells the computer where the string ends in memory. If we take a closer look at the ASCII table, we can observe that the difference between a lowercase letter and its corresponding uppercase letter is consistently 32. For example, the ASCII value of lowercase a minus the ASCII value of uppercase I equals 32. Let's talk about exit status. When your program ends, it returns a number. 0 means the program ran successfully. Any non-zero value means there was an error. You can check the exit status in your terminal using this command, echo $. It will show the hidden return value. We also learned about command line arguments. They let us give inputs to a program through the terminal. Here's what the main function looks like. argc stands for argument count, the number of arguments passed. argv stands for argument vector, an array of strings representing those arguments. This allows us to call our functions directly from the terminal. We can also pass in as many arguments as we need to customize the behavior. In this week's problem set, we built a substitution cipher. This is an encryption tool. The program takes a key with 26 unique alphabetic characters. The letters in the key must not repeat. Each key should include 26 distinct alphabet letters. Then, for each letter in the plaintext, it finds its index in the alphabet. It replaces that letter with the character at the same index in the key. This is a great example of how arrays, strings, and ASCII values work together in C. To wrap up, Week 2 covered some powerful concepts: arrays, memory, ASCII, strings, and command line input. It was a challenging and rewarding week. If you found this video helpful, don't forget to like, subscribe, and come back for Week 3. Thanks for watching. See you next time.